So let's start with a formal definition where we left off last time and remind ourselves that we have these 5 different components that we want to work with. Okay? So this formal definition, wow, amazing, it works this time. This formal definition says, in order to specify all the information I need to write down the state diagram of a machine, I need to say what are the states of my machine. I also need to say what are the possible input symbols, so what's the alphabet, and then I have to determine the edges. So this is the transition function that says from my current state, when I read a symbol from the alphabet as input, what's going to be my next state? Where do I transition? So the transition function takes in a pair that tells us about the state that we're in and the symbol that we're currently reading, and then we'll output the state that we transition to. All right. And then we also need to specify the start state and then those double-circled states, the accept states. Once we've got each of these pieces, we can draw the diagram. All right. So let's probe this a little bit more and ask ourselves how many outgoing arrows will there be from each state if we take a formal definition like this and draw it in a state diagram. And now we have a majority, but it's not consensus yet. Yeah, so there's some people who think that may be different at each state, and other people who feel like it's exactly going to equal the number of symbols in our alphabet. And so how can we use the formal definition to help decide which one of these it might be? Yeah?
So the function delta is defined for the Cartesian product of the set of states and the set of alphabets. That means that it needs to map to a value for every possible combination of a state and a symbol in the alphabet. So it needs to have the same number of characters in the alphabet as outgoing edges.
All right, so the observation here is that the domain of the transition function is the Cartesian product of the set of states with a set of input symbols. So if we fix the particular state that we're looking at, there will be number of symbols, many elements in the domain that need to be specified for that function, whose output needs to be specified for that function. And so in order for our machine to be deterministic, to be well-defined and deterministic, we have to be able to have a computation of our machine on every possible input string over our alphabet. And so we need to be able to say what our computation is going to do no matter what input string we get. Yes? Okay, so with deterministic finite automata, we have to have exactly one outgoing edge from each state labeled by each character in the alphabet. All right? Yes?
So when we have like the self-loop ABC, that's considered to be 3 arrows on top of each other, right?
Excellent question. So when we have this self loop ABC, this is a shorthand for 3 arrows on top of one another. Yeah, so we would count that as 3 edges or 3 transitions. Good point. All right. Other questions? All right, so let's play with these formal definitions a little bit, and let's now try to reverse engineer from a formal definition what the state diagram looks like. So take a minute or so with the people around you if you'd like, and given this formal definition, draw its state diagram.
The definition,
yes.
Do all states have to be reachable?
Excellent point. So the question here, do all states have to be reachable? And the answer is no. There's nothing inherent about this definition that says every state has to have an incoming arrow. Now, that's not going to be a very efficient machine if we have states hanging out that aren't useful, but it's still a possible machine. Yeah, absolutely, good point. Other questions? All right, so we can specify machines in 2 ways, either by drawing their state diagram or giving their formal definition. And so now let's look at one of these machines and try to reverse engineer and understand why it was even built in the first place and what language it recognizes. So let's start with this machine over here. And you might recognize it. It's a prettier version of this one. Okay? And think about what's an example of a length 1 string that's accepted by this DFA and a different length 1 string that would be rejected by this DFA, and do the same thing with length 2 strings.